Let's now take a circuit view of the small signal model. And what will be amazing is that we will put all the math aside and be able to do things in a really, really simple manner. Okay, keep these things in mind. Our basic circuit was a voltage source with an input VI connected across our LED hypothetical device, and the relevant equations were VD equals AE BVD for the total variable. This was the operating point equation, and this was the small signal equation. All right, so let's now draw two kinds of circuits. We can draw a large signal circuit and a small signal circuit. The basic idea is we use math to create and write down the large signal equation, and then we use Taylor's expansion to write down the small signal expression. That can be very, very hard to do for some large complicated circuits. So I'm going to show you a circuit technique that uses circuit analysis to directly write these down almost by inspection. And to do so, in order to create the large signal equation, I'm just going to write down the large signal circuit. And to write down the small signal equation, I'm going to write down the small signal circuit. Pretty obvious. So the large signal circuit simply takes my circuit and replaces the various sources with their DC bias values. Okay, so in this case, I have my LED device, and what I'm going to do is replace the input with its large signal equivalent. So I'm going to get a VI at the input here, and for the device itself, I'm going to get its bias values at the output. So I'm going to get ID and VD at the output. So my large signal equation can be derived from the device equation. ID is given by AE raised to B VD. So writing down the large signal equation typically requires solving a nonlinear circuit. In this case, I could write that down by inspection, but if the circuit is more complicated, I usually have to solve a solve a nonlinear system. Okay, in general, as I said before, this was by inspection because it's a very simple circuit. But if I added some resistors and so on and so forth to the circuit, then I would have to use one of the nonlinear analysis techniques in order to write down the output of the nonlinear circuit. And I could use an analytical method, I could use a graphical method, use computer simulation, whatever, doesn't matter. Okay, I write down the large signal equation and usually by solving a nonlinear circuit. Okay, so next let's come to the small signal response. And here the response, as you saw, was ID was given by ID B times VD. So when you recall, the ID times B was a constant. Okay, and that constant was related to the slope of the function at the point ID VD. Okay, now stare at this equation for a moment. Okay, you see a ID equals a constant times VD. Okay, so where did you see a construct like this before? Okay, where did you see a construct I equals constant times V before? Okay, I hope you haven't forgotten what you've learned so far in this course. It's very, very simple stuff. So where did you see I equals a constant times V before? Well, it was for our amazing resistor. Okay, so where we saw it before was for a resistor. Okay, where if I have a current ID flowing through this, okay, these are my small signal values. If I had a current ID flowing through it and a voltage VD across it, and this had some resistance R. Okay, where by this expression here, R is given by 1 divided by IDB. So all I'm doing here is taking a circuit interpretation of the equation. Okay, all I've done is taken a circuit interpretation of my ID equals constant times VD equation, and that is no different from ID being related to VD according to a resistor relationship, where I picked 1 divided by this as the resistance. Okay, so in this equation, IDB is the conductance of my resistor, and the reciprocal of that, 1 divided by IDB, is the resistance. And the resistance itself is given by this expression, where recall dFVD by dVD evaluated at VD equals the operating point, uh, and the reciprocal of that gives me my resistance. Okay, so what this says is that what you do is you take your function and or you take any element and you find out for small signals, you take the derivative of the function as shown here, and in this particular instance it ends up being a resistor of value 1 divided by I times B. Okay, so for our little device, the current is related to the voltage using a resistive relation. Okay, so this is, let's just stare at this for a second. This is actually pretty remarkable. Okay, what is this really telling us? This is telling us that for this LED device, which had an exponential relationship, for small signals, that device behaves like